All right, it is 3:50, so we will resume. So our last speaker for the day is Bryce Littleljohn, who will tell us more about the status of neutrino short baseline anomalies.
Okay, so hi everybody. Yeah, I'm an experimentalist. I'm not a cosmologist. I'm not a theorist. So it's where I'm coming from. Uh, so uh, yes. Right, we have a beautiful picture of oscillating standard model neutrinos. I just want to kind of give us a background in case there are some, cosmology people in here who are not familiar with neutrino land. Right. We have a lot of experiments that have happened, neutrino physics, and many of them require up this picture of oscillating standard model neutrinos. And this is a lot of different experiments. You see them all named here. I have like instead of showing like the different angles, we put an experiment. I think of it this way. We have L on this axis, which is the source detector distance. And then we have E on this axis, which is like the energy of the neutrino. And what you see is a bunch of different experiments at different energies and baselines. And the ones that have observed oscillations, the ones, these diagonal. And that means we're seeing oscillation at a fixed L over E combination, which kind of looks like this formula right here. So if you are along this line, you're measuring one mass splitting between two neutrino states. And if you're along this line, you're measuring a different mass. And those splittings are different in magnitude. So, you've measured some different types of oscillations. How do we, oh, and by the way, all of these baselines, if you look at human readable units over here, that is like, greater than kilometers lines where all have been detected. Nothing controversial here. And how do we do this? We do this by sampling neutrino flavor. We have detectors that can measure specific flavors, right? And usually, we use this by using the charge current interaction, because charge current interaction will take our neutrino and turn it into its. And if we have some selectivity, we can tell what that lepton is. You can do that, for example, in you can see a track versus a shower. That's muon versus electron, or like in a reactive neutrino experiment, neutrinos aren't high enough in energy to do this to make a muon. So just by seeing anything, any final state lepton, that's what we do. We sample the flavors and then we look for certain flavors turning into other flavors, or we look for certain flavors just disappear. And just to that, here you go. Here's a couple of example experiments. Oh yeah, I'm sorry. For flavors, I like drinking beer. So, maybe an electron is a stout, a muon's a amber, it's a pill, right? So opera is an example of an experimental on this diagonal. Opera, what they saw is muon flavored stuff turning into tau flavor. Camland is an example along this diagonal. Camland was sampling electron flavored neutrinos from a reactor, and they were seeing not some new, but just electron flavor disappear. Okay, so that's your crash course in neutrino oscillations. Now, what I'm going to talk about today is not on this plot at all. It's all stuff that is off the plot. So why would we do that when all the lovely standard model neutrinos are sitting right here? Because there are some strange, anomalies that you could at these lower baselines. And what that means is neutrino fluxes and energies disagree with state-of-the-art neutrino predictions for those. And so this, whenever you see a flavor anomaly, you say, ooh, yay, maybe that's hints for some new BSM physics. One thing you could do is you could draw a new diagonal line, which is apart from the diagonal lines at higher up here and up here. And maybe, in order to do that, you need a new mass splitting. So that new mass splitting, okay, maybe it's not your three flavors of neutrinos. Smoothie, sour, beer, flavor. And that's your sterile neutrino line. could be other explanations. And you know, if BS in neutrino, you know, why don't, you know, how do they behave, right? Do they decay? Do they have couplings to other hidden sector particles? Why not have more than one, right? So my message here is if you crack open a hidden sector, who knows what you'll find? Maybe you won't just find a smoothie sour flavor. Maybe you'll blonde ale or something crazy like that. Okay, so that's a very short motivation why we do this. And why we look at these anomalies. So my goal here today is to talk to you about these anomalies, leaving out the one that Georgia already talked about on Monday. So I want to know just what, I'm going to tell you what the status is as an experimentalist, and I'm going to just try to relate this just to the broader neutrino program and short baseline neutrino program worldwide. So, all right, first I'm going to look at this line down here. This line, the dotted red and black, those are the anomalous results. So down here, we're looking at 10 to the negative. So that's MeV. So the react, and at these energy, about electron, and those electron, so we call that flavored disappearance. Okay, so the one most that. So in nuclear reactors, what is happening? In a nuclear reactor, you're taking something that's heavy, a nucleus that's heavy, splitting it in half, then it's neutron rich. It's neutron rich, so it wants to beta minus decay, and every time you beta minus decay, you get a neutrino. That is what is happening in a reactor. You're making new E bars from these strange neutron-rich fission products. And then those things are traveling through space and time towards our neutrino detectors. Example, just the Diabay far site. This is at Diabay, they had near detectors and far detectors. The near detectors occurred at about, you know, a half a meter, and the far detectors are 2 kilometers. And what you see is if you compare measured neutrino rates at near detector and far detector, and compare it to a prediction you made based on the nuclear physics happening in here, and 1 over r squared, because they're emitted isotropically, you see a relative deficit at the far. That is E disappearance, theta 1,3 mediated standard model oscillations. Have a deficit at this near site relative to be standard model oscillations. That's something else. Yes, this is, this is with the theoretical prediction is the model. Say again?
Okay, if you change to like a KI model, for example,
Change
then
to another
it
model.
pushes down.
I'll get there. Don't worry. Yeah, if you change the model, this ratio, absolutely. Yep. I'm told, and you've heard that the reactor antineutrino anomaly, which is this big set of question marks here, has been resolved. What? Or we've been able to make is we have done sterile neutrinos at looking at it. Here you can see the energy spectrum of interacting neutrinos. And what you would see if you use a detector that spanned multiple lines. In this example, you're spanning something. If you can split your detector lines, what you would see is a different neutrino energy spectrum in each baseline for E oscillation pattern. So this kind of observation here would be a telltale sign that you're what's called of these kind of factors. You can be sensitive to distortions at the same delta. I'm pointing at in terms of one. This is a doped, segmented, liquid scintillator detector at the HIFER research reactor. So small detector neutrino standards. And then here's just a mock-up. This reactor itself, very, very, which waves for these sterile neutrinos on the order of meter type of source. So the detectors that are at small reactors like this are going to do better than detectors that are at large commercial reactors, where the wave will be like. Okay, so yeah, this prospect detector is meters away from an active. So exactly. Broken up. And that I said, where you split the detector up into different baselines, right? So you can try to do this kind of analysis. Now, build that kind of do this same kind of thing. Europe and in China, they're sterile neutrino oscillation results before analysis that was just shared for the first time at Neutrino 24. What has improved in our analysis is we're using the same data set a half a year of reactor data taking cycles and about the same amount of off. Increase the background rejection rate beyond our previous analysis. So here's the 2021 analysis. This shows you in black the reactor neutrino sequence. By just measuring when they're on a signal ratio is not great, not that great. Here's what that looks like. Our improved analysis, you can see how much smaller the red is with respect to the black data points. So that's how Prospect is managed in the past 3 to 4 years by into the experimental to say that just contributes directly to so that means the statistical power of Prospect is basically doubled. 2 neutrons coming into your detector, one of them capturing on hydrogen, one of them capturing on lithium-6. And that there will be the right time coincidence there, the right energies, and that will look. This over here is a high energy neutron coming in a 4-point MeV, and then that neutron will capture, and that also looks like a neutrino interaction. So that's what the 2 peaks are.
Could you also identify the peak around a 5 MeV region that was reported by a diabase and
yes. That we are very positive that this feature here has that bump, but you can tell we greatly improve our. Okay, now the reason we is we wanted to enthusiasts know this very well. Plotting it in energy spectra for each base and L over E ranges. See this kind of wiggliness in the L over E space that Neutrino says is sensitive. If neutrino 4 had seen a sterile neutrino, Prospect would measure this kind of cyan wiggle right here, and the black would be measured. So that, it's here that Prospect's seeing neutrino 4s. Sure. Okay, if you do a more rigorous statistical neutrinos in exclusion, and you can see that we exclude most of neutrino 4 suggested region within 5 sigma. Line is our 5 sigma exclusion. Good for this neutrino. It's best, which is this gallium.
But one very quick question.
Oh, sure.
Where's the best fit?
Our best fit is up here at 15 EV squared. Okay. So it's right in this little dip right there. The delta chi-squared between that best fit point and the null is about 2 units. So if you just do a frequentist test, our data is like very, very consistent with the null hypothesis. Yeah. Yeah. So, so another interesting thing, this gallium anomaly, talk about. And what you see is that Prospect rules out that hypothesis at 2 sigma, basically at all delta m squared lower than 10. So that certainly what I would say is after kind of seems not possible that best and neutrino 4 can be explained by the same simple 3 plus.
On the previous slide, on slide 18, I guess the size of these wiggles has to do with the LOE resolution. Why is the neutrino 4 region so narrow compared to?
It's just because wiggle at this point is very, very fast. And so when you move 5 EV to 7 EV, quite a lot in reconstructed energy. So that's why these wiggles are so fast. And you see the same thing in Prospect, right? We have very, very good sensitivity at like 6 EV squared, and then we have a trough at 7 EV squared.
But Prospect looks a little wider than neutrino 4. Prospect looks a little wider, and I thought that you said that your core was better, so your L resolution is better. So why is it?
If Prospect had you would see similar skinny regions
So
as
the null versus
neutrino 4.
sigma.
Yeah, that doesn't really concern me. That doesn't seem suspicious. You saw a non-zero sigma. Okay. Yeah, and I mean another thing that I think is worth is Nui disappearance searches, if that's what you're into. You can't get better than reactor experiments. I know people try to do Nui disappearance searches and flight experiments with conventional beam, but you just, you can see, for example, here in dotted blue, that's the microboon Nui limits. And I mean, it just can't compete with the. So going to be reactors, unless, of course, there are future ideas. There is a isodar. So an isodar, and then you use isotope production in a target of, and neutrinos you get out of this are a little bit higher in energy. Intensity is just make the intensity of this cyclotron increase. Upon what you can currently do with years. So very nice idea. Stuff. So the whole yeah, exciting that we have an experiment like that. Okay, so now after that, wanted to reactor with no, this reactor. The neutrinos are isotopes. They start by primarily coming from uranium-235, uranium-239 into the fuel, and then you're burning that. So uranium-239. So as you burn, you should be getting fewer and fewer neutrinos. Is we measure that slope. Extrapolate that slope. Plutonium-230. That the goes away when you're only burning 2. So that's an issue. The nuclear fusion. Now, that's kind of changed the theory and experiment communities all still support that this flux prediction issue is true. However, neutrino data doesn't really indicate. The neutrino data, basically, we remeasured this slope with new. In fact, the combined pictures here in those as it was before. So instead of considering the door, so that's interesting, and that's too. And we only be very low. If you do that from very would indicate to you that there is a neutrino being made in the final state that has sterile. And so K measurements and electron capture measurements that are trying to probe space. this plot here. So I'm sorry for the difference in representation. This is just how the community things we're talking about here is substantially high. So here you're looking more AEV sterile, more scale sterile neutrinos. And the two kind of meet such EV squared reactors cut out and weak decay, and these new. Any questions about further comments or
So besides oscillation, there are other interesting, say, targets. No, for instance, I was discussing with Luis Alvarez Russo that LSND, for instance, was conceived not to measure oscillations, but to search for proton strangeness, which is still an open problem. And the last measurement, I think, is BNL 734. So, I mean, this cyclotron, in fact, was discussed as a tool to search for strangeness through elastic, quasi-elastic scattering. Yeah, yeah, just that.
You know, certain solution to focus, but like actually more recently, there's been a lot of other focus on areas. You know, particles. Are we making sterile thing like oh, this example you give is one of them. Sure. So if there is standard or scales that is energy scales that's higher than that, reactors. So the way it's non-standard, you know, couple of those heavy neutral leptons is a little bit lighter. The benefit of reactors is that you just look heavier physics going on. Okay, you know, microboon maybe to look at. And I like to describe it. Yeah. Okay, and think of reactor experiments being like a more direct check on best. And I think people in the community generally tend to view it that way. Because they're okay. So is an experiment that's down in the same region of this plot I showed before. We have chromium 51. Basically, the chromium target in. Now you've got chromium 51. I mean, you compose it to a source, and then you measure its heat release. You know of your gallium 71 bath. So here's a picture of a schematic of what that kind of looks like. So you have the gallium, and then you have your source on the inside. Your goal is to take the neutrinos from the chromium 51 source here at chromium 71. You then recirculate, you let that recirculate the tank, and you count germanium 7 with like a measurement system after running all this and gathering up all the germanium. All germanium 71 with respect to predictions based, knowing your sources, knowing the neutrino section of on gallium. So how to do this experiment? They could disappearing into nu S, right? Or energy of neutrinos thought you were going to. Gallium. Maybe gallium doesn't absorb as much neutrino as you thought it did. Germanium, longer half-life. Okay, maybe the system just isn't super efficient. Like maybe you try and pump all the to counting station and some of it just stays in. Count that. Both the sub-MeV electron reactor nu, the greater than MeV scale reactor beta. Okay, so all of sterile neutrinos, I've just told you that Prospect says that this can't be true. For a sterile neutrino map, that can't happen. P1 decay branching rates, just like base nuclear that was measured in like the 1950s. It's hard to imagine how this is like do this in undergrad nuclear physics lab. Just take chromium. Really nothing you can screw up here. This is the, twisting of the Feynman diagram, helium neutrino capture. This just doesn't seem like a real likely possibility. Germanium 71 half-life. Okay. You mentioned. I'll use a spot on. Systematics. People have looked at this and they're just. There are other hypotheses that are, but really attractive model. But yeah, so this is there, and we don't know what it is. Neutrino 2024 best. Basically, they want to turn to that's different source because maybe there's just issue. Okay, for example, these BSM we're talking here, they apply to a very specific. And also, if you're worried about like the nuclear calculations, okay, things look different for that. Zinc 65 or cobalt 58 is what they're looking at. This is hard because you have to be able to make this source, which like for cobalt 58, understood, or a lot of high energy gammas here, which are much, much, much harder to shield than any chromium 51. So that's like LSND here. So now we're applying appearance anomaly. Energy. Energy. MeV. The way we are going, I'm not going to, I think the idea is you've got something that looks like NUI ABD, an inverse beta decay like electron-positron pair in your detector. That's a hard thing to mimic. You know, I'll interpret it as NUI and interact. Experiment using a lot of instead of being you have a higher SND in theory. You have just the basics of the setup here at JPark forgiving than the previous LSND experiment. And so they basically interest. Well, how is deployed second detector? The second detector is planned to start data taking late 2024. And the first detector has already taken basically four NUI appearance. Yes. A statistic for this accrue slowly experiment. Right here, one of the backgrounds, which is pink background, they have reported on this pink background so far. That's accidentals. That's random stuff, physics events happen each other in space. They kind of so they've uncorrelated backgrounds, and what they see an accidentals rate of 9 times 10 to the negative 8 per spill per 0.75 megawatts, compared to an oscillation signature, which is about of that. What you were expecting based on the plot that I showed you on the last slide. So to make things so maybe we'll in the coming days and prove that at this point of the game. This is all they've shown. The collaboration is hard at work analysis and to measure decay at rest neutrinos, which is interesting for. Okay, so that's what I was wanting to say. Seem mostly dead. Many of them have been well. Most of them are alive and well. After Prospect, it seems not possible that the same simple as one BSL. That is to do this. Awesome, and we react at HE and LEU reactors. Now, in contrast to this clear path forward, its appearance at new E bar experiment, you should expect it to be a lot is experimentally resolved. Yeah, and back to optimism. LS squared is taking some direct checks on us for us on LS and D. The next.
Bryce, we have time for more questions.
Just a comment on something I'm not at all expert in, but you mentioned that after prospect result, best and neutrino 4 cannot be explained by the same simple 3+1 oscillation model. Just regarding neutrino 4, there's been already several years ago a paper signed by different collaborations, maybe including prospect, I don't remember, saying that the analysis done by neutrino 4 is not serious at all. So I think this has to be mentioned. I'm not an expert at all, but they seem to be extremely clear about the fact that this is not serious and one cannot take this as a serious analysis. Okay.
Basically, all the other short baseline experiments have lots of questions about this neutrino core analysis. One thing I will say is that the neutrino core experiment is not done. They are building upgraded detectors that will be, in theory, more sensitive than the ones that they have previously built. So that's one argument I think I would have for needing other experiments like Prospect 2, is if we question the results that came from Neutrino 4 before, we're going to be having new results from that. So we're going to want equally powerful data from another source, from another group of people, so that we can get some cross checks.
Sorry, I just had a quick clarification on your gallium bullet point. So you're saying that the sterile interpretation of the gallium anomaly is probably out, but the actual experimental understanding of it is still up for grabs. Am I interpreting your whole arc correctly?
Order, basically what I want to say. Carlos has papers about the idea that maybe you're seeing some oscillation decoherence effects in the short baseline reactor spectrum experiments that would then basically reduce the power of the prospect style analysis. But it doesn't escape the fact that the deficit in flux from reactors is only about 5% at most, while the deficit from BEST is 20%. That is not reconcilable. Decoherence. So I think there is a.
You're the chair, so you get.
Yeah, just a comment on that, and that for any model, 3+1, 3+2, 3+3, as long as it's vanilla sterile neutrino, you can't expect differences in disappearance probabilities measured with neutrinos and antineutrinos. Any differences, observed differences, would be effective CPT violation.
Yep.
So it depends on how bold you are in coming up with alternative interpretations, but that's the kind of effect that you need to reconcile the two.
Yes.
Right. I have a point about. Sorry. For the reactor antineutrino measurement, you guys are inverse beta decay, but I have a paper looking for carbon-13 neutral current scattering instead of inverse beta decay, which is quite sensitive for the especially 5 MeV because the excited state of a carbon-13 star can emit the 3.685 MeV photon.
Yeah. And
then by looking at those signals as well, I think you can definitely identify the origin of the result at all. Yeah.
Okay.
And we can also have some prospects in terms of a few evolutions. So.
Okay.
Yeah.
Great. I'll take a look at that.
On the JSN square, you have this accidental background per spill.
Yeah.
So how is the accidental separated from the signal? Is it just energy difference?
So what you can do is basically take Because what you're doing in an inverse beta decay measurement is you're measuring a prompt looking thing, which is like a positron, and a delayed looking thing, which for JSNS squared is a neutron capture on Gatella beam, which is basically a gamma cascade with 8 MeV total energy. So what you can do is you can look for that first thing in one spill, and then in the next spill, you look for the delayed light thing. That is those are clearly going to be not physically like correlated, right? Because one's in one spill, one's in another. So in that way, you can kind of directly measure the random coincidence background. And that's what they're doing in this paper. But I'd emphasize there's a lot. The name of the game in IBD experiments is just like trying to zoom in on the E+ like signature and zoom in on the delayed NGD signature. So the more cuts you can make on that, the more of these accidental backgrounds you can rule out. So I would bet that JSNS folks will over time figure out whether it's like a machine learning, like a BDT estimator that can like really home in on E+ and NGD looking signatures. And that's what I look for them to do. I'd imagine they will.
And my second short question is, you talk about the source experiments best, and you said that they will divide their experiment into 3 regions, and that was easy. Is that what they are doing first? And is that a timeline for that?
So you need both, because the chromium 51's half-life is like 50 days or something like that. So they're not making a new chromium 51 source. The next source that they will make will be whatever this new source is. It's unbelievably difficult and dangerous and like, yeah. So you won't do one without it.
Okay, thank you.
You probably learn something interesting if you could do that, but I don't think that's the plan.
Yeah, I also have a question again on GSNS squared. I mean, the same question, I mean, following the question asked by Carlos. So if I understand correctly, GSNS squared is trying to better characterize these accidental events that could mimic inverse beta decay. But I'm a theorist. So naively, I would have thought that this is already well understood, no? Because inverse beta decay has been the basics of all these reactor neutrino experiments that have been done since 1960, 56 or something like that.
Yeah, no, it's not the beta decay. It's not the beta decay that's the problem. It's the analysis tools and reconstructed physics. Now, so it's like, like basically JSNS squared is just one of the diet beta vectors just moved to J part ML. So if everything were perfect, you just say, oh, just use all the same exact diet beta 6 variables, and then you'll like. In practice, it's not that simple. Like the electronics are totally different. So so now you have some low-level thing and like reconstruction you have to do, and that just takes time. JSNS squared is not a very large collaboration. In the United States, there is a single and in Japan, I think there's only. So it takes time. I'm sure they'll get there. They're just not there yet.
So the brain is not the process itself, it's the analysis.
Yes,
okay.
Yes, definitely.
I had a question concerning the BEST experiment. Curiosity, what are the main sources of the systematics? And why, I mean, such a difference between the older measurements and the new one? I mean, do they make an assessment on the systematics?
They do. I don't know the details. In this paper right here is a really nice one. Basically, first off, the best collaboration had like PRL and the PRD. The PRD is very, so if you have questions about these systematics, they describe details in that paper. And these guys then subsequently take, 30 pages to sort through all of those details again. So I don't know those details off my head, but I encourage you to take a look at that paper.
Okay, and the other was a comment, I think, sterile with the delta M square, which is so large as 10 TeV square or larger, would have several implications. So
Sorry, say it again.
from all the exclusion curves, we see that we are now able to take out most of the area of the anomalies, for example.
At low, yeah.
But large delta M square, like that are left above that, would have other implications.
Yes, I mean,
So,
I'm not an expert in that. Like,
such
either
delta M squares would have several implications.
Yeah.
So, unlikely.
Yep.
I just have a very naive question. Will you plan to detect the higher energy neutrinos, for example, 10,000 GeV? Because the neutrinos can be very high energy in the universe, especially in the very early universe. So I just see the S cube can reach then about 2,000 GeV.
So that is for the experiments that I'm talking about. These are the wrong. The detectors you want for that are the neutrino telescopes, where these are rare events, and so you just want to build not a ton scale detector, but like a gigaton scale. So these you're not gonna you don't really need to worry about those, and you're certainly not making those neutrinos in a nuclear reactor.
I think that's very important to detect the very high energy neutrinos in the future. Yeah.
Okay, a last burning question, perhaps? Or do we not have time?
Yeah. Okay, I have also, just a comment. I want to repeat myself. I think a bit disappointing in the exclusion curve by GSNS that we don't see the Karman exclusion curves, because I see that there is this nice, sort of nice bend out, and I think that is also out from the, I mean, it's a pity that I think they don't put the exclusion curves by Karman. Yeah. Because I think it would be very instructive. And that region there, which is out, I think it was already sort of out before.
Yeah.
So.
One.
Okay.
So let's see if I understand the implication of that. So from what you, it seems like there is like an order of magnitude between what they expected and what they are seeing.
It's not.
It's not?
It is not. So when you give that number that I quoted here, and again, I'm not a JSS squared collaborator, so don't quote me on this. I'm just, the range they're talking about is 20 to 60 MeV here to here. So in that range, if you compare blue to pink, what you're expecting is like, yeah, like 3 to 1. And instead you're getting like
2 to 1, the other way around. So it's like 6, 8 or whatever. So, yeah. So would that mean, so let me understand correctly. So this would imply that either they reduce that or the experiment is useless.
It would, I mean, it will not be useless, but
well,
it just
they wouldn't check.
Inherently, you're just going to have lower statistical power.
Yeah, but then you don't prove LSND region.
Yes. Yeah. If you can't improve that situation, it's not.
Okay, we're way over time. Thank you everyone for the questions and the great discussion. This concludes our session.